Our next speaker is Humberto Campins, also from the University of Central Florida. Seems like a conspiracy from the SOC.
Yeah, we're taking over. Okay. So today's talk is going to be about predicting space weathering effects on primitive asteroids and the results that we're getting based on our spectroscopy of inner belt families, which we started about 8 years ago, and we're getting some very nice results. But before I go into the details of this talk, I wanted to tell you a little bit more about CLASS, that the principal investigator of CLASS, who just preceded me, asked me to put in this talk. So we have the Center for Lunar and Asteroid Space Surface Science at the University of Central Florida. We have 14 co-investigators, 35 collaborators. University of Central Florida and the Florida Space Institute are the lead institutions, but we have 2 NASA centers, 11 universities, 3 observatories, and 5 research centers. Dan organized and hosted a couple of interesting seminars. Last year it was on ISRU, and this year it was on asteroid sample return, and these are online and available to all of you. And so now I can start on my talk. So the space weathering of primitive meteorites is showing some very interesting results. In the last 5 years, there have been some really interesting laboratory results, and we have been observing these asteroids that are in the inner belt, which are the source of most of the NEAs, and we're getting some interesting results there. So I'm going to tell you about those, and then I'm going to tell you about the implications for asteroids Bennu and Ryugu, and then I'm going to give you the conclusions. But as many of you may already know, I usually give the conclusions at the beginning of my talk, just in case somebody has to leave or falls asleep. So we have 2 sample return targets, Bennu and Ryugu, which are dynamically and spectrally most likely from the Polana family on the inner belt. I'll give you more details about that in a second. And the agreement between our spectroscopy and the laboratory research has points to older terrains on both of these asteroids expected to be bluer than the younger terrains. So it's the opposite of what you get on ordinary chondrites, and it's also the opposite of what you would get on all other primitive meteorites that are not CI or CMs. So there's a very good paper by Kathleen Lanz, Rick Binzo, and Francesca De Meo this year, but Lanz et al. Have been working on this since 2013, and basically what they're what they're telling us is that for CI-CM meteorites, we get that space weathering is going to make things bluer, brighter, and more convex with time. And this is very interesting because meteorites that have an albedo of 5% or lower are going to behave differently from those that have higher albedos. And so we have observational evidence that is consistent with this. And we have that for 2 pairs of families so far. The Clarissa Polana family in the inner belt. Clarissa's young, Polana's old. And we also have that for the Veritas and Themis family, which are young and old respectively, which are observational results that are consistent with these laboratory findings. I'm going to be concentrating only on number 1 today. And what you have here is the inner belt, and you have semi-major axis versus inclination for a number of families, which are on the left panel, and in the right panel is the background. And you can see that the Clarissa and the Polana family are close to each other in this orbital element space. And the Polana family is the largest in the inner belt. It is spectrally homogeneous, dominated by C and B type asteroids. It does not have the 0.7 micron feature. None of the objects that we observed, and we observed about 60 of them in the Polana family. It is the most likely source of Bennu and Ryugu, and that was the topic of my talk last year here. Here's the Clarissa family, a much smaller, younger family, and it is similar to Polana, because it is spectrally homogeneous. It has, none of their objects show the 0.7 micron absorption, but there are subtle differences that are very interesting. And these are results that we're just publishing this year. And essentially, it is that the Polana family has a larger percentage of B-type blue asteroids than Clarissa family. And the space weathering effects on primitive asteroids can explain the spectral differences between Clarissa and Polana members. So this tantalizing agreement between our observations and the laboratory results, it has testable implications. In other words, when we get to Bennu and Ryugu, we predict that the older terrains will be bluer than the younger ones. And if you see here, the Clarissas that are plotted, if this thing, the B types are about 33% of their membership, and in the case of the Polanas, if this thing ever works, is so over here. The Polanas are 45%. I'm sorry for the online audience, but this pointer doesn't work so well. So what have we found? So I'm going to just recap that Polana is bluer and more convex than Clarissa. We don't know if the albedo has changed. We cannot detect any differences in the albedos between these two, but we're working on that. Basically, the albedos are identical within the uncertainties, but we may be able to reduce those uncertainties. So Bennu and Ryugu are the targets of Hayabusa 2 and OSIRIS-REx. Our Earth-based observations and other Earth-based studies will establish a broader framework that will maximize the spacecraft results. And we know that Bennu and Ryugu are most likely from the inner belt. Work by Bill Botke and collaborators show that the majority of the near-Earth asteroids come from the inner belt through the new 6. And so Polana is the most likely source of both of these objects, based both on dynamics and on spectral characteristics. So my conclusions again, sample return targets are most likely from Polana, and our spectroscopy and the laboratory work agree that older terrains are likely to be bluer than younger ones. Thank you.
Looks like we have a few questions.
I thought that your plot of populations versus spectral types is interesting. And the biggest difference between the two is the abundance of X types, which goes with what you're talking about is moving from redder to bluer. And just a reminder that all of these spectral types are based on spectra rather than mineralogy. So you can easily have minerals that look like X's and look like B's and C's, and literally in the same sample.
Correct, but since I don't have a little pickaxe and I don't go on field trips to asteroids until now, and we don't know what the mineralogy is, and that's why the sample return will be so interesting. So a question to you that I didn't have time to ask you during your talk. So when we bring back these samples, you're going to be able to give us an idea of the thermal history of the different grains in the sample based on the composition or the dehydration of the kronstatite?
The short answer is yes.
Okay.
The long answer is with ease.
Okay, and can we practice between now and 2023 when the OSIRIS-REx samples come back?
Sure.
On your meteorites?
Yes. I will be happy to give people who analyze grains samples of dehydrated grains.
Quick comment. I think I know the answer, but I think it's important to point out over which spectral range are you talking about things being bluer or redder?
Yeah, that's a good question, and let's see if I can. Yeah, so it's basically between the visible, which would be
0.4 microns.
Yeah, about 0.4 to about 1, and then it turns over and it becomes, it's miles towards 2 microns. So 0.4 to 1 micron would be the blue part.
Okay.
And
Thanks.
then the bottom of the smile and then turns up. I think Bill has a question.
I'm closer to the microphone than Carly. So you showed a relationship between Clarissa and Polana in terms of the fraction of B-types. But Polana's a really big family, and Clarissa's really small. So I can imagine that the size of the objects you're looking at has to matter. Have you done that same fraction in terms of size to see how it changes? Does it change as a function of size?
Yeah, actually, it turns out that once you get below the largest fragments, you're sampling about the same population. So, and we were using the GTC, the Gran Telescopio de Canarias, for the visible spectra. So we ended up sampling about the same size objects, which were the ones that were bright enough for us to observe. So yeah, that's a good question, and we can do a more careful D-bias. But yeah, we have about 30 objects in the Clarissas, and we have about 60 objects in the Polanas. And so we have better statistics with Polana, but yeah.
Yeah, can you explain a little more what you mean by younger and older? I
Yes.
suspect it's linked to space weathering, but I'm trying to understand, with this new image we have of these kinds of asteroids, what is young and what is old on those surfaces?
Bill? I can answer that, but you have an expert here on the...
What's younger?
Yeah, I mean, Clarissa is less than 100 million years old, but we don't know how much. Polana is about 2 billion.
Oh, okay. I guess I didn't grasp Carly's question. Yeah, I mean, the families have a very distinctive shape in terms of their semi-major axis versus size. And so you can use what we know of the Yarkovsky effect to date these families. And so Clarissa is just a small family, and yeah, my memory is it's a few hundred million years old. And Polana is much, much older. So was that the question?
Yeah, I understand that about families. What I'm interested in is on the surface of the asteroids itself, because we're getting close. And you said younger terrain should be
Yes.
blue and
Yes.
So how? What's that mean?
That's a good point, and I hope that we will have clear evidence of what's old and what's young. But who knows? We may not have. I mean, if we have a clear landslide and we have two color units, one in the freshly exposed material and one in the the material that has been sitting around for a long time, we will have that. But it could be that we have a completely uniform asteroid. It could be that there is, so.
Well, what we saw this morning, or yesterday morning, is there's big blocks and there's finer stuff. So if it was a soil and a soil recently overturned, I can understand that. But we're talking about blocks and non-blocks.
Yeah, and I'm relying on Dan Shears to tell me where I'm likely to find a recent landslide. But the point is, until we do the morphology and the spectroscopy together, we will not know. But if we have a clear crater, and the crater is less blue than the older terrain around it, that's what we're hoping to find. Does that answer it? Right?
We have time for